In this video we're going to be taking another look at surface developments. If you're watching this video, I'll take it that you have already mastered the basics of surface developments, and this is more of the intermediate and advanced side, which will take us right up to some leaving cert higher level style questions. The one little tip I would give about surface developments, when you're approaching questions, or you are practicing the topic, or you're trying to master the topic, is that every single time you create a surface development drawing, there's just two things that you need to be thinking of all the time. Every single line needs to be a true length, so it's all true lengths in the drawing, and every surface or face that you draw needs to be drawn as a true shape. If you keep that in mind throughout all surface development problems you are drawing, it will really stand to you. It will really help you and ensure that you don't fall into the pitfalls and some of the basic errors that might be made on this topic. So, keeping true lengths and true shapes in mind, we're going to approach our first question here, and in this question we are asked to draw the complete surface development of the cap, keeping the number of joints to a minimum. So right here is a piece of an aluminium cap that will be put on a post, as it's shown here in the image. A single piece surface development. So a surface development is not just simply a case of fold everything out flat and put them all in separate parts of a sheet of metal. If this was made of steel, you're not going to weld on every single joint, because that's going to take too much time. It's going to cause areas of weakness. It could be causing voids for moisture and dampness to get in, and it's just going to be much more inefficient and more expensive to create and to manufacture and produce that part. So what you aim to do is create all of these parts, any sheet metal parts, or maybe it's packaging from some products. You aim to create the parts with the minimum number of joints possible and the minimum length of joint possible, and we don't call it joint, usually we call it a seam. So where it joins back together is called a seam. So let's just get started on this one. I'm going to be keeping in mind my true lengths and true shapes here. There's really two ways of solving a question like this, and I'm just going to go through the most efficient way first of all. The free space right here is just enough space for me to go ahead and draw this surface development of the object here shown in the elevation and here shown in the plan. If you don't have these worksheets, well, the elevation given is 48mm long, 12mm tall, and a total height of 27mm up to the apex. And then of course the plan is going to be, what did I say, I think it's 48mm both ways on the plan. So that's the overall sizes of that plan and elevation if you don't have this sheet yourself. What I'm going to do is this: I'm going to find out what the true length of any one of these lines here, because I know that from the apex of this pyramid top down to any of the points here on the top of this base part, it's going to be any one of them lines here, for example, is going to be the same length as all of the other ones. So I'm just going to go ahead and find the true length of one of those lines first of all. And I'm saying that I'm finding the true length, but I'm also doing something different, so I'll do it first and we'll talk through it then. To find the true length of a line in plan, maybe if I just go and call that A for apex there, 0.1, 0.2, 0.3 and 0.4 there, and then that's my A for the apex here, and this is 1 and 2. They're both falling in line with each other, and then we've 3 and 4 falling in line with each other. To find the true length of a line, I'm going to do a rebatment, not an auxiliary. I'll rebat it onto a position parallel to the vertical plane. I'll take my compass, I'll fix the apex in this case, and I'll rebat up into its position where it's parallel to the vertical plane. What am I also doing? Well, I'm also, if we wanted to look at it a different way and use different terminology, I am inserting that pyramid into a cone. So depending on how we'd like to actually term this, I'm either just finding the true length of a line, which is a basic way to look at it, that we're just finding the true length of a line by rotating it up, and I'll just finish that part of the process first of all. And it goes from 0.1, of course it doesn't change height, so the height just goes straight across, and that will give me, I'll just use green just to keep it color coded, A across to that new point 1 right there. So that would be, if I was just calling this, finding the true length of the line using a rebatment there, it would go from A to 1, for example. But if I was going to talk about this in the other way, and the way I prefer it, I think, is it right there, that dashed line is this green line along here. Okay, I might call that point 5 right there. That from A down to 5 is the extreme generator on a cone. And that cone contains the pyramid. So I'll take up the second side of the cone. That cone right there contains the pyramid. So if it contains the pyramid, it means that the generators of the cone are the same length as the edges of that pyramid. So two different ways to look at this problem. I've now put a cone down over the pyramid, and I know that any generator on the cone has to be the same length as any edge here on the pyramid. So that's a handy way to look at it as well. So whatever way you're used to talking about these questions, you go with that, whether it is just a true length of a line or the inclusion of a cone to go around the object. I'm going to go with the cone, I'm going to call it the cone, but same principle from here on anyway. I'll take the true length of the edge of that cone of the generator, which is also the true length of the line that goes from A to 1. Now I know that that distance I just set on my compass is the true length of, it's the true length of A down to 2, down to 3, down to 4 and down to 1. So I'm going to start off at some point over here in my sheet, and I'm just going to pick a point and I'll just center it in the space I have roughly, right there. I'm going to call that point A. So that's the apex. From A, I'm going to just take the true length and swing it. Now, I need to pick a position to start here. So, I'm going to start anywhere, really. It doesn't matter. I'll just take a completely random position, and I'm going to start there, and I'm going to call that from A down to point 1. So that's the edge A1. I'm going to first draw this orange surface. So I'll just add a little bit of colour down here. That orange surface is the first one I'm going to add. Now, the true length of A to 1 I've already drawn. I'm then going to need the true length from A to 2, which I also have. It's here someplace. And what else will I need? I need the true length from 1 to 2. So to find point 2, I have to find the true length of 1, 2. Now as I look down on my plan, I get the true length of 1, 2. It's already there. It's right there for me. So the true length from 1 to 2 goes from point 1 over to point 2. So there we go. That's point 2. And I'm gonna keep this light now for a while until we get into our line types. So there's 1 and 2. So that is one surface. So why did I go that direction and not up this way with 2? Well, when you draw a surface development, you're supposed to be looking at the inside of the object, not the outside. So if I wanted to look at the inside, I'm going to have to go from 1 up to 2 and draw this first. Hopefully this will make sense as we work through the sheets if you haven't come across that before. So while drawing the inside of the object, I would have to start by going here to the right. Next, I'm going to go ahead along my surface here from 2 to 3, so I'm looking for this next surface. Bit of colour added in first. Now, what we'll find here in some objects when they're regular is that I already have my compass set and I left it set because the distance from 2 to 3 is the same as 1 to 2. So the distance here from 2 goes out to 3. And we can mark that. Now, I think some people will already be getting the hint here that you can go ahead and mark from 3 to 4 and 4 back to 1 if you want. I'm going to go now and just do them one at a time. I might just speed up the video a little bit and just put them all in one at a time, add some colours as well just to code them. We'll always take the distance as well, and we just need to make sure that even though we've used points 1, 2, 3 and 4, they're all there. Some people will make the mistake and stop at this stage, not realising that we always have to close it back in to the first point. So 4 always has to return back here to 1. Although those 2 points are coming quite close to each other, they shouldn't touch. If this is a pyramid, they shouldn't touch. If they touch, it means it must have been a flat surface at the very beginning. So there's 4 back to point 1 right there, and a bit of colour to add here. And there we have the first part. So that is the 4 sloping surfaces. Every single one of them is a true shape, and every line marked is a true length. Now I'm just going to change up some line types here nice and quickly. I'm going to put this one in as a continuous solid line, and this one in as a continuous solid line. I'm just going to call that SEAM, seam edge, and I'm going to call that also seam edge here. Those 2 edges would be welded together if it was sheet metal, or they might be just taped or glued together if it was maybe cardboard. So what I'll also do is this: I'm going to just change the type of line I had. I've them in very light to 1 long, 2 short, long, 2 short, long, and it's, you know, it's just something technical. It is nice to see it in a drawing. So starting and finishing with a long line, and it's long, double, short all the way through then. So 1 long, double, short. Big difference between these, of course, and hidden detail, which is all short. There we go. Now what I also need to do is I need to get the base surfaces, so these vertical surfaces here, to drop into my development someplace as well. What I look at there is the angles. So from the base edge of any of my triangular surfaces, I need to go off at 90 degrees by a distance as given in the elevation. So I'm going to attach the 4 base surfaces to the end of each triangular surface. Now there's loads of ways to do this, but there's only one efficient way, and this is it. So what I'll do is I'm going to line up first of all with the edge there, 1/4 my purple, and then I'm going to use sliding set squares so that I can utilise the 90 degree end of my set square here, run off up to the other end, just getting caught on my stand here, so I have to go a different way, up to the other end here at number 4, and run off. How far does it go? Well, again, it's a true length, and where do I see the true length or the true height of that surface? I see it just here in the elevation, so the height is right there as given, and I'm going to just step it up. Now I can step it up at both sides if I want, but I prefer not to. I'll step it up at one side only, and I just get my sliding set squares back in play again. And while I'm here now, I'm going to make this a fold line, because the second surface has to fold about that edge right there. There's a fold line, and there's a continuous line set out at the distance marked using my compass. My seam lines. And they're going to be joined back onto the rest of the edges of the object, or surfaces of the object I should say. I'm going to just repeat that task now for the other 3 sides. And there we have our complete surface development of the capping. Now what we would find there is that if we grab a scissors and if we can cut along every solid line, and if we bend every fold line, well, we would end up getting complete surface development, or we would end up getting the complete 3D shape exactly to the dimensions given right here. What we would also find is that this would be the inside of the object. So if we were folding it, and if I cut along right now, cut this out of my page and bend it, I'd be bending these edges here up towards me, and this would be on the inside of the shape, which would make sense with my colour pattern and with my label and number pattern. That is it for this particular question. Nice easy intro there, and the only little thing to note here is that another relevant answer here would be something like this. Okay, if we set out and started off with the 1, 2, 3, 4 base edges folded together, that would also be, in a sense, it's a correct development, but is it an efficient development, and does it really answer what we're asked to answer? If you owned a business, would you allow someone to design your packaging or your steel caps, in this case caps for decking posts, just like that? No way you would not, because it would be so inefficient with the amount of waste material you'd have here, and also with the amount of labour that would be required to then further manufacture that part. So although they're both correct surface development, this one here is technically much better. So it's much neater, more efficient, and it's more, I suppose, economical use of material. So we always try to look for the most economical use of material and of space on our page, rather than big development spread right across the sheet. On to our next one. So now here in just this question, we're looking at the practical example given here is the plan and elevation part of rocket. Is shown, just a toy rocket there, and it's based on a hexagonal pyramid which has been cut as shown. So when we look at our elevation, it's clear to see that the pyramid is just inverted, and it's also truncated, so it's cut there at the ground. But what I'd like to do first of all is just imagine that it's not cut, and we'll just go ahead and really lightly, I'll drop this in maybe in a colour here. I'm going to start off by saying that what would it look like if it wasn't cut. And if it wasn't cut, we'll go right down here maybe, and on the second edge we'll go right down as well. I don't think I even went far enough with that first one. Go right down along to there. So if it was not cut, and this is what I'd always do when I base something on a pyramid or a cone, even if it's inverted or cut, I'd like to see it if it was full. That's how big it would be. Okay, so that kind of gives me a good hint. That gets us started on this. What am I looking for this time? I'm looking for 1, 2, 3, 4, 5, 6 faces of this object, and all faces are exactly the same. Now, where does that leave us? Well, we have a couple of options. We could tie the development onto the view that's already given, or we could maybe make use of the free space we have down here and have the development completely separate. But whatever method I decide to take, this pink detail right here is going to help me. I'd like to also just start off by, down here in plan, I'm going to just lightly go across, and I'm going to just find, again, where would the centre of this object be if it was a full pyramid that wasn't cut, and this would kind of lead me along the way to that. So that would be the apex of it, which is clearly it's stuck right down here on the ground in this case, but there we have it. So what do I need? I need to put a cone around this again. So I'm just going to imagine, just like the last question, we're dealing with a pyramid here. I'm going to put a cone around this object, but this time it's even simpler. So if I grab my compass, and I'm going to turn this inverted pyramid into an inverted cone, and what we'll find is that it actually makes no difference at all. We didn't actually have to draw that yellow detail in there. Why not? Well, the reason we didn't have to draw it in is, what do we see? The extreme generator of the cone, which is going from the apex over here to point 1. That extreme generator, which is seen as a true length in the elevation, goes from point 1 right down along to the apex, which is down here. So what that means is the edge that's already given from the apex there, I'll call that A, which is down here, the edge that's already given from A up along to 1 is already a true length. So we can use that. What does that also mean? It means that on the way from A up to 1, we have this point here, point 2. But will I number that? I won't yet. I'm going to go around here actually, and I'm going to go this way from 1 to 2, 3, 4, 5, and 6 working my way around here at the top. So that's 1, 2, 3, 4, 3 and 5 line up, and 2 and 6 line up. So I have all of my top points. Down below then I'm going to use 7, 8, 9, 10, 11 and 12. So they're my pairs of numbers that correspond to each individual edge. So I have the edge that goes from 1 to 7. I have 2 down to 8, so 2 to 8. Then it'll be 3 down to 9, 4 down to 10, 5 and 11, so 9, 11, 6 down to 12. And there we go. What we need to look at is this, okay, on the way from the apex up towards point 1, and we know that from the apex up to 1 there is a true length. Well, on the way from the apex up to 1 we grab 0.7 along the way, and that is also A to 7 is a true length, and 7 to 1 is a true length. So it actually makes this question quite easy in a way. What I'll do is this, I'm going to first of all take the generator of my cone, the extreme generator of my cone right there, and I know that that's a true length, as I said, from A to 1. Where do I have space here now is the big question. I'm going to keep this down close to my border, so I want to just keep it well down there and just in the free space that I do have. So I'll just mark my point that I know will work. Well, at least I think that one right there being point A should work just fine. And that's a completely random point. Anywhere you want to put that on the page, you can put that. As long as I said, as long as it fits. So there we go. That's the true length from A to 1. Let's pick a point 1. And like last time, anywhere you want. Pick a point 1, drop it someplace, and get started. So the first one I get, and I'm going to keep it light, is A down to 1. And what else do we need? Well, along the way from A to 1, I'm going to go back to my true length right here again. From A to 1, along the way we have 0.7 right there. Okay, so again I'm going to go from A and swing down to 7, and I'm just missing my plan right there, which is good. And there we go. So on the way from A to 1 I get 0.7. And what does that give me? That gives me one of the edges of the object. So A on the way down from 7 solid as far as 1. Let's get the first surface first of all shaded in, and second of all we'll then go ahead and start drawing. So there we go. What are we looking for next? We're looking for the distance from 1 to 2, and again, if it is in a horizontal position here in elevation, well, it must be a true shape down in plan. And this guy here, if it's cut by the horizontal plane here in the elevation, it must be a true shape in plan. So our hexagons in plan are true shapes. Now the distance, first of all, I want to go from point 1 on to point 2. Again, being mindful that I'm going down there to point 2 because I want this to unfold into that. So 1 down to 2. While I'm here, I can just keep going if I like. So that's 1 down to 2. And then I know that, as I said, 2 to 3 is the same size, because it's a regular object. Then we have 3 to 4. 1 to 5. 6. And we have used all the points, but we don't have all the surfaces. Don't forget, it goes from 1 to 2, 3, 4, 5, 6, and returns to 1. What's next? 2 options. I can take my distance from point 7 to point 8, which is on the smaller side, and I can start marking from 7 on to 8. That will work just fine. The second thing is, I know that the apex joins to every point. So the apex there joins to 2, and along its way it catches point 8. And we can see where the compass strike that I marked and the line that I just drew correspond perfectly. So I'm going to save myself a bit of time here, and I'm going to do this. I'm going to join it down to all points. And I'll just switch pencils out, and I'm going to go heavy That's the extreme edge or the seam. I'll take it from A down to 0.6 and I'll draw my fold line. A down to 5, 4, 3 and 2. And there we have it. That is more or less our complete surface development. The ends are not round though. All of the ends are straight edges. And of course the inside shorter edges here are also straight edges. Finally, I'm going to add a little bit of colour, so the surface 1 to 2 here, and along to 7, 8 is orange. And working around here to the front of the object, and again we're showing the inside of our development when we unfold this guy. We're taking it, just in case anyone wants to get really technical, we'll take it that the colour of the surfaces here is inside and outside, okay? Because as we look down on plan we're seeing the inside, and as we look up at the elevation we're seeing the outside of the surfaces. And there we go, that's this next one finished. This time we're going to be looking at a cylinder, which is usually quite an easy object to work with, because generally before, when you'd have studied maybe the earlier stages of developments, if you were working with a cylinder, you'd always know that they were actually quite easy shapes to work with, because usually you were given the elevation of the cylinder standing on the XY line. Maybe the top of the cylinder was even cut, which would increase the difficulty somewhat. But if it was cut, that still wasn't really an issue for us. We were given the plan view. And we always had our stretch out line. And the only issue with this is that usually we learned that, you know, you had your stretch out line and your seam, and your development might look something like this. But we always kind of learned that the stretch out line might maybe just went across in line with the base of the object. But in fact, the big thing we need to know is this, that it's the axis of the object, the central axis of the object, which is the line that goes down through the center of this object, from the center of the plan of the base to the center of the top. That central axis gives us the direction of our development. So if we took our cone, and if we had an incline with our cylinder, and we had it inclined, well, the development is going to be perpendicular to the central axis. The development of this cylinder right here will go perpendicular to the axis of the object. How does that work down here? Well, we have the axis, the central axis of the object going through. So our development can't use a stretch out line that goes across the sheet. Our development needs to go up perpendicular to the axis. Our lengths in this case will all be coming from our broken up circle, which is presented already for us here on the sheet. I'm going to first have a quick look at SolidWorks just to see this. I have this object modelled up on SolidWorks. I'd like to have a very, very quick look at that. The solution is there as well, with the development just stretched out and flattened in SolidWorks. So let's flip over there for a few seconds and see what to do first. Now here in SolidWorks we can see the cylindrical tube. In this case it's from a kid's playground. A slide from a kid's playground. So we can see the cylindrical tube here and see exactly what it looks like. It is, if we just look in at the elevation quickly, it is a cylindrical tube that stands down at an angle. It gets cut here vertically, cut with a vertical plane here at the top, and it's just cut with an incline, simply inclined plane here at the front. What we need to look at is this though. The development, as I already just noted there, as I sketched through, the development is going to move perpendicular to the main axis running through the object. What's it going to look like now? I haven't drawn through a full solution. I'll do the solution on paper, but That's what the development looks like, and if I just move it up out of the way there so that we can see it, there it is. The length of any line on the development is the same length as any line that lies on the surface of the cylinder, and the lines we're using then are going to be parallel to the axis. So a series of lines that lie on the cylinder parallel to the axis are going to be moved up perpendicular to the axis and plotted out to form the exact development as we can see here. The length, the total length of this object right there is the same as the circumference of any circular portion of the cylinder. So the length of this development right here is the circumference of the cylinder. So there we go. That's it just on SolidWorks, just quickly shown there the flat surface development of this cylinder just using a flatten pattern, surface flatten on SolidWorks. So let's get back to paper and let's get drawing. Now we're back on here after seeing this just developed out there and flattened on SolidWorks. So let's start working through it now. In this case, we're kind of lucky enough that in the worksheet I have here, it's already structured for me. We already have the circular portion drawn, which would be the true shape of the object, the true shape of a cross section through, and it's also drawn right here. That makes it quite handy for us, and it's also numbered, which is really good. Now the first thing I want to say is this, okay, point 1 is at the very top. It's the very top of this slide, or the top of this cylinder here, point 1, which is why it's not up here. That's the back of it. This is the top of the object here, as we look down on top of it, so 1, and then 7 at the bottom. Point 4 then will be out here at the front of the object, so we have to imagine that this is the axis and this circular portion here just rotates out to us. In most cases you would draw this circle right here, you project up along with your axis and you draw it in line as an auxiliary view showing the true cross section, and we'll have to have a quick look at that after. So let's just get going for now. The first thing I'd like to do is I'd like to actually draw what the front of this looks like, because it's incomplete at the moment. And how will I do that? Well, first off, we'll have a look at point 1, which references the top edge on this object, which gets cut by a plane right here. And where is that? I'll just take it down to plan. Point 1. And then 1 goes in to hit. So that gives me, just note that one, that is point number 1 right there. What else do I already have? That's point 1. I know that point 7, which is along the base of the object, goes down and hits the ground, which is through the center right here as well. Point 7 on the ground. I also want to find another 2 easy ones to find there is 4 and 10, which are along the center of the object. 4 out front near me, as we can see, 4 out towards the front and 10 at the back. So we have 1 and 7 done. That is 4, 10. I'm going to just project that point right there where 4 and 10 get cut. I'll project them down, and we see that they're already plotted out at the correct distance for us. So that's point 4 where it gets cut. That's point 10 where it terminates there at the front. Then we have the rest, and if I don't need to redo the work that's done for me here. 6 and 8 line up along the 1, and then 5 and 9, 3 and 11, 2 and 12. All of those points are going to be translated down along parallel to the main axis. We have now created a series of lines that lie on the surface of the object. Okay, so right here well, it's actually number 3 and 11. 3 and 11 are lying as a line on the surface down along there. The one out nearest is probably going to be 3. The one back at the back of the object is going to be number 11. So that is 3, 11. This is 2 and 12. So we have 1, 2, 3, 4. So that's going to be 5. 6, 7 is the base. 6 and 8 line up, and then 5 and 9 line up. So if we think about it, starting at the top, going 1, 2, 3, 4, 5, 6, 7 to the bottom, and then we go to the back of the object, and it's 8, 9, 10, 11, and 12. The movement of all of these lines right here, which lie on the surface of the object, they're all parallel to the axis, and parallel lines are parallel in every view. So 3 and 5 parallel to the axis, 2 and 6. What have I now? 8 and 12. 1 and 7 are already done, of course, and then we have 11 and 9 finally, all parallel to the axis. And let's see where they finish. So 2 and 12. And if you need to take a bit more time about a job like that and just keep referencing and keep checking, then please do. I know that this is going to be number 2, goes down, number 2 comes out, so I get number 2 right there. This was 1. I'm going to get number 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And using that series of points, I'll just freehand it in. There we go. That's that freehand curve just dropped in there nice and quickly to the front of the object. So we're looking at the top of this slide. We're looking at the front of it going around to the base. This is all the inside surface of the slide right here. That's all inside. And then finally going around the back of the object and right back up the top again. Let's start developing. I'm going to set, in this case, I might just set my adjustable set square because it'll make it a bit faster for me. I'll set my adjustable in line with the axis. And then I can project off at 90 degrees to the axis. I'll just start off at the moment with points 1, 4, 10, and 7 along the back of the object, and I'll just do the same here at the front. 1, 4, 10, and 7. I'm going to start my development now in any position I want. So I never like to tie development onto a view, because I like to just stress that it is a separate view, or it's a separate drawing of the object. It's not necessarily tied onto a particular view. Now, why did I start there with the edge 1, 1? The reason I started with that one is because I know just by looking at this that 1 to 1 is the shortest seam on the object. Okay, and we always try to keep our seams as short as possible. So 1, 1 there is the shortest seam on the object, which is what we want in this case. Okay, so the shortest seam on the object, the shortest seam edge is from 1 to 1. So I just moved out any distance at all you want to move there. Just move out random distance and get started. What do we need next? We need the distance up to number 2, okay, or line number 2. So we have the line number 1 already on the object. I want the true distance from 1 to 2, and that's not shown here in the elevation. That's not shown here in the plan. 1, 2. It's only shown in a view that shows the true cross section of the object. So what we're looking for, and I suppose some people have probably realized this and have gone on ahead already, we're looking for the distance from 1 to 2 right there. Okay, and that distance 1 to 2 can be just marked up. Now, if you prefer, in this case here, you can just start marking up through a center, just a reference line that we could drop in here, which is what I'm going to do. I'm going to take just a completely random line, 90 degrees to that seam edge, which is also 90 degrees to the axis, of course. And I'm going to mark from 1 up to 2. The distance from 2 to 3 is the same, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we are not finished because I didn't get back to point 1 yet, so it has to go back there to point 1. The other thing to note is that we have to start and finish on the same edge. We have to start and finish on 1, 1. I should actually just number these along my way here just to make sure I get them all. So that's 1, 2, 3, that's line 4, line 5, 6, 7, 8, 9, 10, 11, 12, and yeah, that's okay. I had them all in there. So there's all of my edges. It's going to start and finish on the same one. So number 1, dropped in again, and there we go. Time to start putting all of our other markings in. Again, my adjustable is set parallel to the axis. So where is 2? Well, I need to do some more projecting first of all. So I'm going to need to project, and if you feel more comfortable just projecting and doing one at a time, then do that. I'm going to just drop them all up there now, and then find all of my points on the freehand curves after. So what are we looking for? I might just need to do some more notes here. So that is 2, 3, 4, 5, 6, and 7. And then it's 8, 9, 10, 11, and 12. Now that everything is noted, it should make it somewhat easier for me to find my points. Some people would prefer to go ahead and do this and just draw all of their lines in first full size and then find their points after. Some people would prefer to just find them as they go and figure out exactly where they're supposed to be at. I'd be easy enough really. I wouldn't really mind which one to do. I know that that's 7, and I know that 7 is the shortest one here, so we could just do that. These lines that I'm drawing right now have to be light because there are no fold edges or fold lines on a cylindrical object. Or you could argue that there's an infinite number of fold lines, but there's no hard edge, so we can't draw it in as a fold line. It is only a construction line. That's point 1, point 1, point 7, point 7, and we have point 1 and point 1. That's a good start. After that, use whatever way of visualizing this that you like. You can draw all of these parallel lines if you want, or you can do what I'm going to do, and that is going to be one at a time, finding the correct start and correct finish. And there we have it. There's the complete surface development of that truncated cylinder right there. Though this question here to the left is much simpler, it can be somewhat, I suppose, hard to visualize what's happening there. I'm going to go ahead and just do this question really quickly. So, to get going on this one, I'll just line everything up. And when I line everything up, I realise that there's maybe a little error here in the sheet, so top lines up fine. The entry area to this line lines up just fine. The ground obviously does, but this line here doesn't really serve any purpose at all, so I'm just going to assume that line isn't there. Why is it that the edges aren't doing anything for me then? These points right here, well, that's the finish point of this straight portion of the side walls of the slide. So the straight portion of the side walls come down to here and then slope off to the ground, which just looks linear, because I suppose we're assuming that these walls have no thickness for the sake of this drawing. Same goes for the plan with those points. In plan, we're assuming again that that's just where the side walls are going straight down along and then sloping off to the ground. Let's do the same thing this time. Use the same knowledge from here and same understanding and apply it to this question. So really quickly, and that is the very first line on the development. And what does that line represent? It represents, I'm going to say points 1, 2, 3 and 4 is the 4 points on this first surface. Now I'm going to add some colour to that surface as well. And in my development I have started off with point 1 and point 2, which is on that blue surface right there. What do I need next? I need points 3 and 4. Quite simply, the blue surface is already a true shape, but I'm just trying to ensure again that I show the inside of this object. I'm just going to run off up with a perpendicular line right there. That's going to be my line that I take all of my dimensions along with my compass. What is the perpendicular height of this surface? Well, it's already shown here in the elevation. As I said, the elevation there is a true shape, so that's the surface. And I'll mark it. I'm trying to flip this shape backwards here now, so it might make sense soon, hopefully. And again, it's all down to this showing the inside surface. And there we have the first part, fold line done. That gets us from point 2 up to point 3 and from point 1 up to point 4 right there. So 1 joins the 4, 2 joins the 3. And we have our first surface. Next one then to add in would be the actual base of the slide, the part you sit on, so it's here. Now, what are we thinking this time? Again, it has to be a true shape. It has to be all true sizes. So I'm going to number this one. First of all, we had 1 being up on top here, and we had 2, and under 2 was number 3, and then right down here on the ground was number 4. I'd like to then number this guy 5, 6, and then up top, of course, will be 7, and then finally point 8 right there. So that would be the back, the comrade of this blue surface here, but I need this green one along the way. So let's go and do that. So the distance, first of all, from 4 to 5, the width of this part of the slide is here, 4 to 5. Or I can take that, and again I can mark it from 4 to 5 and 3 to 2, or probably my favourable option would be just get the adjustable. There's going to be another surface tied onto this, so And there we go. We get our distances there, and we get the very front of the mouth of this slide here. Little bit of numbering to be added in, so up from 4 there is 5 in the green, and what did I say was at the back is 16 is on from 3. I'm going to then add in, what colour will I go with this time? We'll go with a red. And what am I calling the red? Well, I'm calling the red this, the one that's behind the blue right there, or we're seeing it there as an edge view and plan. So we'll just call it the right hand side wall. So if you were standing up here, if you were looking in from this direction, on your right hand side would be the red wall, which is shown here in the end view. That red wall of the slide right there. The red wall is the exact same size as the blue one, because they appear to be directly in front and behind each other in the elevation. So we'll take the size of the blue one, step it up for the red one. And there we go, bit of colour, we're finished. So that's that question finished right here, that's that sheet finished. So if we're looking at any regular objects such as prisms or cylinders, and if the angle is not, if it's not standing straight up like you would generally have seen maybe at junior cert level in most cases, if it's turned at an angle, well, the projection of the development needs to be perpendicular to the main axis that runs through the object. So when we label the axis of the object, or the central axis, well, all projections are going to be perpendicular to that axis. Now, let's get on to our next question. Next up, we have a question based on an envelopment. So the difference between a development, which is when you fold something out flat to find the true shape of all surfaces, and an envelopment is when you have to take an object and actually just basically wrap it on. So the wrap can be in the form of a label, for example. So it could be a label that you're asked to wrap onto a cylinder or onto a cone. Or the envelopment can, in this case, it is giving us, we're already given the true shape. So usually a development is to find maybe a true shape, but in this case they're telling us that that is the true shape of the opening that's made on these Easter egg boxes here, and we need to wrap this true shape back onto the object. Now, what does that mean for us? That means that we're just working backwards. We're taking our knowledge and working backwards. Now, what I'd like to start off with is this. I'd like to start off by recognizing that here's the true shape of, I'm going to call it a label for now, even though it's actually a cutout. I'll just call it a label because I think it's easier to understand if we think of it as something like a label, something actually tangible that we can see in front of us. We are looking at a hexagonal prism here that just comes from the ground up, and we have a label in this frontal position right here, and it's stuck on already to this front surface. How much of the front surface does it cover? Well, all it leaves is this part right here, down at the bottom. And it leaves this part right here. So that is the surface of the front surface of this prism right here. That is the remaining area of the front surface. I'm going to just number this as well now. We'll just work our way around with this. And I'll just call that edge 1, edge 2, edge 3, edge 4, edge 5 and edge 6. So from edge 1 to 2, that surface, well, all that remains is covered there in blue. Okay, so what I need to do now is I need to wrap it on again and see what I'm left with. Okay, there's two main ways that we can do this, and it's all down to, I think, personal preference, really, what you would find easier. The first thing is we can wrap the label, or the second thing is we can unwrap the object. So whatever you would prefer. What I'll do is I'm going to wrap the label. So where's the label binding is what I'm looking for here. So the label, or the wrapper here that's in the front, well, it'll bend at point 2 and it'll bend at point 1, and this portion of it will bend around point 1 and this portion will bend around point 2. So let's see how that works. I'll take my compass at point 2, I'll take the entire remaining wrapper and I'll bend it. Okay, how far does it bend? Well, in this case right here, it bends until it is in line with 2, 3. It bends into that position right there. What happens next? Well, it bends once more. Now obviously the elevation isn't finished, but I'll get back to that. It just bends once more. So it goes from point 3, it bends and it goes around. Oh, sorry, bit of a slip there. From point 3, it bends once more. From there, and we take it and we bend it in. So we know that the label finishes at that point right there, because we've just fully wrapped the entire remaining length of the label from 2 across. We've wrapped it once onto this straight line, and we've wrapped the remaining on again. So there's my label in its wrapped position, or in this case they're telling us that it's the true shape of an opening, but I'm going to think of it as a label for now. What does that look like in elevation? That's the next question. So in elevation, I think that the easiest thing to do is this. I'm going to just imagine for a while that I'm just looking at this end. So the end of it was all the way out here, right there. That was the end of the label. Well, the bottom point just came straight in along to this area right here. It stops right there. So that's the bottom point. And the top point of the label also came in around. From here, it came in. So that is the very back portion of it right there. Along the way though, we're going to have a lot more work to do. I need to do an unwrapping now for a minute again. I need to see this. I want to see where it bends around at point 3. So I'm going to unwrap that down to my label, to my original position. I'd like to know how far along the label does it hit point 3 when it hits it there, at that exact position. How far along the label does it hit point 3? So let's take it, and we're going to be looking for the position of the label as it wraps around a 3. Well, originally it was here. Okay, that was the original position, but then it wrapped in around and got as far as edge number 3, which is right there. So what are we looking for? We're looking for where's the top curve. Like, the end of it is simple because it's all going to be one straight line. It goes across the front, it goes out to the edge number 3, and it goes back in along the surface and finishes. But the top of it is the harder part. So we're looking at this at point 2, it's hitting here. At point 3, it's hitting here. And at the very end of the label, it's hitting here. And I need to join those points together some way. It's going to be a freehand curve. Let's see what that looks like. What am I dealing with down in plan? I'm looking at there's about 36 mil there down in plan. So what I'm going to do is this, and we don't have to use equal divisions or anything like that. I'm going to say that I want a point 12 mil and a point at 24 mil, which will be just 2 equally spaced points. And then on this side, I might just say that's about 18. I'm going to go at 9 mil there and put a point here as well. So what are they? What have I just drawn? I've just found some points that are on the original label up top and on the original label up top here and here. And I would now like to find points A, B and C. I'd like to find them in the wrapped position. So let's wrap them on. So we can take a selection of random points and we can wrap them onto the object. So from 2, I'm going to wrap on point C, I'm going to wrap point B, and I'm going to wrap on point A. A is not there yet though, because don't forget and don't make the silly mistake of taking A all the way around to here, because by the time the label hits point 3, it's now unrelated to 2. Everything hinges about point 3. And there we go. They're the 3 correct points where C hits, where B hits, where A hits. We project C up, we project B, and we project A. As we originally discovered here when we wrapped all the way around, and I'm going to call that point D, the end of the label, D. D. As we discovered, as the label wraps around this object, this is the vertical edge, so the points move horizontally across. So that goes across. B and C. What do we get? We get point C in its position, point B in its position, and at the back, point A. You can add more points in if you like. I think that's going to be enough really for this drawing. But what do we end up with? We end up with a freehand curve joining out there onto the edge 3 and joining back in here to the end at D. Now this is an opening, so I'm going to draw it as such. I'm going to draw this as an opening. So I'm going to heavy in what needs to be heavy now, and then we're going to just take a look at what this ends up looking like. And there we go, that's the left side done. What I'm also going to do is I'm going to say that the inside of this object is green. I'd like to just differentiate between inside and outside here so that we can hopefully understand this. The outside of the object is blue and the inside is green, so I'm just going to have to stop there until I complete my right hand side. And it is symmetrical, so it will be the same, but you might just get a chance to see it all again. This right here is all cut out, so we can't add any colour right there. That would be maybe your clear plastic cover that goes on over it at that point. But the inside is green, the outside is blue in this case, which of course also means that this edge along here is going to be seen as one of the solid inner edges of the object. And this object, this one here, the same. I'm going to go ahead and do the same thing now on the right hand side, but just instead of starting off the way I started last time, just let's think of it in a slightly different way. Let's think that we're going to first of all unwrap the surfaces. So we unwrap that surface first, and we could also unwrap this surface if we wanted to. You know, just a different thought process about this might come in handy for a particular question. So we'll unwrap both surfaces. So that would be the two full surfaces unwrapped in line with the label. The label finishes here. So let's wrap the label. I'm going to take maybe an extra point or 2 points this time. What I'll do is I'll go in pink colour this time for my labelling. And I'm going to go at 9, 18, 27, 36 there roughly, and then I'm going to just have maybe 6 and 12 mil here. Now, does it really matter? No. Just do whatever you're comfortable with, whatever will work and whatever will be accurate enough. 2 and 1 is appropriate. I would always prefer just maybe to have an extra point in here, but let's just go for it now. I've already used A, B, C, D, so I'm going to go with E, F, G, H, I, J, and K. I have quite a few points this time. This is going to be busy. I'm going to find all those points in the label's original position in the elevation. And now I'm going to wrap all those points down in plan. So taking it from point 1 onto E, F, G, H are all the easier ones to start with. I'm going to wrap point I back on to the open position, point J to the open position, and point K to the open position, which is the end. From here I'm going to further wrap from point 6 there, which is where the label, and I'm going to keep going at the label, folds around. And I'll wrap what are these points I, J and K onto that surface. Now I have all of my points in the original position in plan, in the original position in elevation. I have wrapped all my points in plan and found them in their new positions. I suppose I should label those new positions. So E, F, G, H. We have I, J and K. Time to project. And there we go, all projected. And let's show what the wrap looks like here in the elevation. So position E goes onto the new E. And if you want, you can just dot them as you go along. Or we could have just done them one at a time, so it's really down to personal preference. I'm going to go ahead and just grab the first point that I've done. Before it gets confusing, I'm going to go and get the one on the crossover and at the end. I'd find those to be the easiest ones maybe to get. So the one at the end, where is that? It is here. The one at the end. I'll just, while I have this pin in my hand now, I'm going to go label as I go E, K, and H then is the one on the crossover position right there. H. So at the front I need F and G now, so F just happens to line up there with the edge. That's only by chance really. F and G taken up onto position F. And G. So we have the front point here, which is, what's that, on the edge number 1, E, F, G, H, and then I need I and J. So I'll take my heights across for I and J. And the wrap position in plan. I, J. It's free-handed in. E, F, G, H. And H, I, J, K. And K is the end of the wrapper, which drops straight down. Here's the edge. And a little bit of colour to add, and we'll be on to the final part of this drawing. So, the blue surface. And the internal green surface. And there we go, that is the first part of this question. So there's the complete elevation showing the opening in its correct position. So that is, or if we like, it's a label wrapped around, but obviously if it was a label we wouldn't have the same pattern of colour happening here, and we'd have more hidden detail around the back edge of the label. And that is the first part. And the second part that we'd like to do here is we'd like to just develop the blue surfaces of the object, or I should say the blue or the green, I suppose. We'll just develop the object. We'll exclude the top, exclude the base. Now, it is a prism. It's a prism that sits on the horizontal plane, and the main axis through the prism stands vertically. So if you have a vertical axis, as I said in some previous examples there, the stretch out line, or the direction of my development, is going to be at 90 degrees to the main axis of the object. I'd like to just find that axis and drop it in. I don't need this for the drawing, I just want it for clarity and just for a bit of continuity in my teaching here. I'll find the axis first of all by splitting up the object there in plan and drawing the central axis here in the elevation. There's the axis through the centre of the object, so my development is going to stretch perpendicular to that axis. Now, where should I start? I have to start my development on any shortest seam. So, technically the shortest area on this object is right here at the front. But we're not going to cut it there and create a new joining. We might just default to number 1 or number 2. It doesn't really matter, whichever one you prefer. So I'm going to go on out here. I wonder now, the next thing I'm going to just check quickly, I want to make sure I've space. I think I have one edge here is about just under 40 and there's 6. So yeah, there'll be plenty of space out here to the side on the worksheet. I'll pick a position, just keep it close. Pick a position to start with. I'm going to start here by calling that edge number 1. How much of the object is remaining at number 1? Well, we only have this small bit down below and a small little piece up above. So at number 1, we have the small portion below and above. We are opening this guy, obviously showing the inside, so I'm going to be going next to number 2 if I want to show the inside. Is that correct? Yes, it is. So 1 on as far as 2 right here, 1 on to 2, so 1 on to 2. And what does it look like at 2? Well, we're lucky enough that we have everything there in the elevation, so at point 2, well, it's going to be the same as 1, isn't it? So we can just project across again. So from 1 to 2, and that is going to be just a hard edge right there. And then there's number 2 in the elevation, same as number 1. It's not going to be a hard edge though. Now that's going to be a fold line, so it's hard to show the fold line detail here. Just try our best to drop it in. It's not going to be a one straight line though, because it's curved between 1 and 2, it's curved. So I'm going to get back to that after. Okay, I'll do as much as I can before I have to deal with those curves if possible. I'm now going to plot out all of the other flat surfaces, so going from 2 to 3 and so on. So 1 to 2 is done, 2 to 3 to 4, 5, 6, and of course coming back to 1 again. I can number them. And I'm just going to project some verticals, which are going to be the locations of where I drop my edges once I find out exactly how long those edges are. So number 3 is here, it's on the edge, the extreme left. We're still just going, it's all cut open, so 2 goes along again to 3, which is quite handy. That shows my fold line down below. What about the top of 3? Well, it gets cut right here, so I'll project that across. This time at the top of 3, what's it going to be? Coming from 2, it's another curve, so I can't do anything with that just yet. Okay, so I'm going to leave these top parts until after. Working on to number 4. Well, number 4 is completely untouched. I know I have my cutout still to do. I'll get onto that in a while. Number 4 is a complete edge right there. It's not cut, it's not disturbed in any way, so we can just drop that in as a full fold line. Number 5 is the same. What happens at number 6? Well, number 6 gets cut top and bottom. Top and 6, the bottom is there someplace. So 6 down at the bottom is here, so I'll fold that, and 6 up at the top is here. I should have my height line taken a little bit further there. And what am I back to? Number 1. So we have to finish the same way we started. We're finishing up. We've gone from 1 to 2 to 3 around the back to 4 to 5, 6, and we're finishing here on this same seam edge again. So I need to just project whatever I have at the start to the end. If you do what I'm doing here, dash it and dash it. Make sure you show those dashes. Ideally, I suppose it's probably best just to project in case in case you do happen to go off. At least if you project, you will know straight away if you've done it right or if you've made a mistake. We want to make sure as well that we're always credited for the construction work we do, and it doesn't look like a guess at any stage. So I think showing the full construction line is a more sure way of doing that. What I'd like to find now is I've gone from one around to 2 to 3. From 3 on the way to 4, I want to find the end of this opening there, D. So what I'll do is this. I'll take the distance from 3 towards 4. And I always just talk my way through it. From 3 towards 4. I don't want to go the wrong way from 4 towards 3. It's from 3 towards 4 is the end of the label. Okay, so, or the end of the opening in this case. From 3 towards 4 is D. So, where do I find that? That is D right there. And where is D in the elevation? Well, the top of D is here. Take it across. So that gives me a little bit more information again. And I get the end at D. There. So that's handy. Maybe I'll just, instead of working on those curves, I might just go ahead here and find what one have I that label as point K. So where is K? On the way from 6 towards 5, which that happens to be the very same, of course it does. 3 towards 4 has to be the same as 6 towards 5. So on the way from 6 towards 5, I get point K, the end of that label right there. I'll take my height. We'll find it. K has to be the same height as D right there. So that's the end of the cutout on the right hand side. I can go ahead and heavy in the rest of that base of that cutout. Time for some freehand curves now. And as you might have already guessed here, based on the exact principle I just implemented right there, what are we going to be doing this time? We're going to be taking maybe from 2 towards 3. I'm going to take point C. So from 2 towards 3 gives me point C. And I'll be keeping the fine liner in my hand here, or pencil if you want, and label as you go. From 2 towards 3 I get B. From 3 towards 4, that's kind of hard to get that small, so I'm going to go the opposite way. From 4 towards 3, I have point A. So from 4 towards 3, sorry, from 4 towards 3, I have point A. Don't make a foolish mistake like I was just about to. So there's C, B, A and D all there at that side. So let's go and find them ones. So lines marked and heights transferred from the elevation. There's A, there's B, there's C. Make sure we get them in the right positions. A is the bottom one here, and A is up. That's A, that's D. That's the crossing point where it goes over to the edge. Then we have B, cross, B, up. We have C, cross and up. And then we have where it crosses the edge. Now we're going to need this same curve as we have here as well, of course. I'm not going to take many points for that. You know what, I might just drop that in after. For now, I'll just add these guys right here. So there's the two of them complete, 2 portions. Maybe we'll go for this side next. I've extra points to take this time, so I'm starting at point 1 and going towards point 6 and grabbing all the points along the way. So 1 to E, 1 to F, and 1 to G. And this time again, it's going to be really hard to set the compass so small, so I'll go from 5 towards 6 and get I. So from 5 towards 6, I. And from 5 towards 6 was J. Heights transferred, points marked, and another freehand curve. Now, there we go. I just know from the practice with this that I can just transfer and say, right, that's I right there. Sorry, that's J, isn't it? Yeah, J, I misread. That's J along there, that's J up here. And we'll see that if we go I, that was H, that was G, F, E, in the beginning. And we get this nice, smooth, freehand curve through the whole development right like that. And there we go. Finally, our very last little portion right here. So, best thing to do I think here is from the center, first of all. From the center of the object, halfway between 1 and 2. Halfway between 1 and 2. You can easily drop a point in. And that point is just here. And at this stage now, you can go ahead and drop extras in if you like. I'm quite sure that anyone that has got this far in the video will have no problem in just plotting an extra point between maybe one extra here and one extra here if you feel like it. Or I'm just going to go ahead and freehand it in. And there we go, that's the complete surface development showing the inside of this object, having wrapped our label or wrapped our true shape of the opening onto the object. Now, just for reference, a little bit of colour added there, just showing the inside of the object, and I think we can probably imagine wrapping this thing back up again and creating the object itself. That's that one finished for now, so let's make a move again. Now here we have on SolidWorks our next development, and I suppose what we could say is that this is like a first of a transition piece. And when I say transition, I mean it transitions from one shape to another. Now this is quite a simplistic example of a transition piece, because it just goes from rectangle to square. Later on we'll be seeing some that maybe go from rectangle to circle, and that's when things get a little bit more interesting. But for now we're going to go with this. Something like this would have a typical application, like I suppose the common one would just look like a cooker hood. So where you're increasing your surface area down low for gathering steam over a hob or cooker, and then reducing it up higher because, well, number one, it looks more aesthetically pleasing, and number two, you're starting to come in and finally form maybe 100mm round duct exiting and taking the exhaust fumes from your hood. So that would be your typical application. In industrial applications would be more like air conditioning units and venting and so on, where ducting and venting, where you might be transitioning from one shape to another, and it might all have to be made out of sheet metal. So that would be just some real life applications. Just if anyone is going drawing this one at home, it's actually quite a simple one to set up, really. There's the setup of the elevation. Now the yellow surface in elevation lies directly in front of the blue surface here. If it can be visualized there, the blue surface at the back is a vertical surface. So as we see the elevation, if we see that blue surface, as we see the elevation, it's the true shape of the blue surface. So as we look down the plan, the square, I'm going to call that the top of this piece of ducting. The square top of it is centered along the back surface and just tied to the back surface. So there we go. That's what we'd start off. What we would start off with now is this. We take that blue surface, and because we've drawn it in an elevation, we would just pop that elevation exactly as it is and drop it up there. I would just drop it off onto the vertical planes where I put it, but anywhere at all in your sheet. Okay, so you take your elevation because it's true shape and just drop it up there, redraw it. We were not asked to draw this throat section up here, so we just leave that be. But I know on the worksheet I'm working on here, it's already labeled for me. So I think that the top points are, the base points are A, B, C, D, and then it's E, F, G, and H. But that back surface there is G and H up at the top, and C and D down at the bottom. So G and C, if we just have a look, G will be this point up here, C with this point down here. So I think that's probably the next thing I dropped on there, was those two labels for G and for C. And then what I would like to be able to do next is this. I would like to be able to take this red surface, grab that red surface and fold it out straight and drop it on here beside the blue one. So I'd like to be able to do, essentially unfolding the object onto a flat surface. To do that, I need some points. So what do I have? I have point G and I have point C already on my development. I need points, what have we? B and F. How do I find them? Well, I find them basically using my compass. And as I started this whole video with, developments is a series of true lengths. I would take the true length from C to B on my compass. And from point C, I would strike that true length off with my compass, just anywhere, no idea where it goes, just strike it onto your page. I would then say, right, where's my other fixed point? So I have a fixed point G and a fixed point C, which I already have, and I'm searching for point B. So I took the distance from C to B, and then I'll take the distance from G down to B. So I've just created a triangle from my two fixed points G and C, and I've taken two lengths out to B and out to B. So I've created a triangle. That's why this method is called triangulation. I need to find then the true length of this blue line, and once I have it, once I find that true length of the blue line, I bring it up, I strike it from G, I take the true length of the blue line and I strike it, and where the two arcs cross, I have the true length from C, the true length from G, and that's my point. And there we go, point B. Now you're probably going to get the gist of this very quickly and realize that it's just more and more and more of the same. Okay, and the same principle solves most of these transition piece problems. Next one, if I want to finish off this red surface, I need point F. So I take the true length from G to F. I'd set that on my compass and I'd bring it on up and swing it. There's the length from G to F, just swung out there randomly. finish my triangle from my fixed point G. Well, from my fixed point C, I need C to F as a true length. That pink distance right there, find the true length of it, set it on the compass, and swing it from C up to cross the original arc. And there we go. That gives me point F. I have point G and F. I have point C and B. That means I have a red surface. And there we have it. Now, we keep working out along. After the red surface comes, what have I? Yellow surface. So the yellow surface is going to be tied on here at point F and at point B. So what do we have? Point F and B, and we're going to tie this yellow surface on. Let's add some extra labels on there. We have a fixed point F and we have a fixed point B, and we're searching for A and we're searching for E. So again, we're back to triangulation. Formulate your triangle. From F, get your true length. From B, get your true length. Set them on the compass, bring them up, and strike them off. And that gives you a point. You know where this is going at this stage. From your fixed point up, from your fixed point out, you get your, sorry no, two true lengths. I just jumped on an extra one or two there by mistake. You get your true lengths, you mark them, you label your points, and you draw your solid. Finally, around to this side, the green. Now I could easily tie the green one on here, but I just decided, you know, I'll just keep the chain going as I'm going here on SolidWorks. So just to reinforce, point E and point A are my fixed points. And what am I looking for? I'm looking for point H and point D. So from E and A, which are here. There's, I think that's E up top and that's A down the bottom there. Well, first off, I'll take my two true lengths again. So it's just, again, it's more the same. Two true lengths from E down, from A out. And mark them on your development. And then do the same up to the last point we're looking for. And once we've gone up to that point, we mark them with the compass on the development. We get our fixed points. And there's the surface. There's the green surface finished. So let's get back to paper. We've seen there how a selection of true lengths, and by formulating all of these triangles using triangulation, we can complete this question. So back onto paper, let's see this one unfold. And here on paper we can see the same sample question that we had there on the on SolidWorks. So here's our question. I just went with the same lettering system as is already shown here. Now on green there in paper, you can also see that a lot of the work is kind of done for me, but I'm going to just redo it because I don't want to be messing about here and kind of using what's already there. We'll go for it. So we'll see what we're dealing with. First of all, this back surface is my blue surface, and it is a true shape as shown in elevation. Of course, the A, E, F, B is not the same shape because it slopes away from us. But the back surface is the true shape shown in elevation. So that's kind of handy. It's already started for me and it's dropped down here already. So that was done for me. Okay, all I would have to do, but right now it's just taken and translated down along my page, which is quite useful as well. That wouldn't really be a big deal if we had to do that on a blank page. Working from here though, once that blue surface is done, okay, that blue surface at the back, which I can't really see, it's just there as an edge view. I think the colours I went on to next in on my model was that I wanted this red surface here next, and then it was around to the yellow surface to the front as far as I remember. They were the colours, and the green then to the left. So to find that red surface, I need, first of all, I need to take a distance from C to B and from G to B. So I'm going to search first of all for point B. I'm going to take the distance and I'll just set it here. I'm going to use colours for everything. Maybe not necessarily the same colours as we had in the video, but I'll use colours for everything. I'll take the distance from C down to B. Okay, that's a true length. It's on the ground. And I'll swing it from C, and I'm looking for B out here someplace. No idea where it is. That's the first one. So that's distance from C to B. Now you can note it in there if you like, you know, just dash it in or something. C to B. Only if you want to. I find that might get a bit confusing. I'm then going to do this. I want to cross over. What other fixed point do I have? Well, I have C and I have G. So from G down to B. And I want to take this distance here. That's the diagonal through the object. But the big question is it the true length? Okay, so like I said at the very beginning of this video, every shape has to be a true shape, every line has to be a true length. Is that a true length? No, it's not. So I need to find the true length of that line. How do I find it? Well, the easiest way, I could use my full auxiliary view. That's a lot of work. I'm going to fix point G and I'm going to rabat the end of the green line down there at B. So fix point G and rabat. So rabat the end of the line. That end that I just rabatted represents point B, which moves horizontally. Had some change. So where am I now with this thing? That's the new point B. Or that is point B, which gives me a true length. That right there is the true length of G to B. Setting that on my compass. G to B. Setting it on my compass and using it and striking it off. So there we go. All that work gives us what point? Point B, right there. Point B, I can just join it up to C right now if I want to, and I can just get started. I can see some progress from my work. There's G to B, the base edge of the object. What you're going to find is that a lot of people might start fast forwarding the video now because you realise what's coming. Okay, it is a lot of the same, but I'm going to keep going for now. Next, I'm going to search for point F. Okay, so first off, I'm going to take the distance from G to F. It's a true length down in plan because it's a point view in elevation. It's horizontal or it's parallel to the ground. So G F is a true length already. So I can just strike G to F. I'm looking for F out there someplace. No idea where it is again. That's the distance GF. And what's next? Let's grab a different colour. What's my other fixed point? Again, I could use B, but I'm not going to. I'll just use point C back here. I want to find C to F. Is that line a true length CF? No, it's not. So, once again, time to do a rabatment. And, you know, rabat in, rabat out, rabat whatever way you want. I'm going to take it there now. And instead of going out and overlapping it nearly, I'm just going to go in with this one. So that's C to F. I fixed point C, I moved point F, it falls perfectly on the center point right there, which gives me true length of CF. TL, CF. And if I have a true length, I go and use it. I just made a mistake on that one. I'm going to have to just rethink that one for a second. Point C is here, point F is here, so that's point F, of course. So that's a big mistake there. Make sure not to make that one on paper. That's what happens when you're pushing through a drawing too quickly. Point C is fixed, point F just moved, and there is the correct TL of the line C to F. So good thing I spotted that now, otherwise I'd have been gone forward here wondering what was happening. So that is the true length line, of course, from C up to F. There. And what do? I take point C and strike it on. And where that blue and red cross gives me the point I'm looking for, F. Time to, what do I join? Join up G to F, and that's going to be a solid line. I don't need to put this extra piece on. And F to B is the end of my red, so long double short again, and that's the end of that surface. So that's the first one done. The good news is this is symmetrical, somewhat symmetrical, in that I can move around to my yellow now, but if I want, I could maybe attach a surface here over this side. So I'll just add a different colour to that one. So that I'm going to call that a green surface there. The true lengths I've already found are common to this side as well, so they will work as well. So we just need to, I suppose, have a think about them really. I'm going to just kind of push through this, maybe forward on this portion, but what we're thinking of here is this, the distance from C up to F is the same as the distance from D up to E right there. Okay, the distance from G down to B has to be the same as H down to A. So if we can save ourselves some work, we certainly save it. We're going to find the mirror image now. Same surface, just mirrored across to this side. Final surface is the other one. So first off, maybe drop a bit of colour on it again. And let's go for a couple of true lengths and let's drop this on. Looks like there's not going to be space over here off my green, so that's why I put a solid edge on that, and I could just label that as another seam edge there. So whatever will end up being tied back on here. So I just need to go ahead and find points A and E. Now I already have them here on the green. That's no good to me though. I need A out past B. I need E out past F, and I'll draw my yellow surface here. A couple of true lengths and we're good to go with this one. First off, B to A, distance from B to A, swung from B, searching for A out there someplace, and then the distance from F to A, but of course as a true length. So what will I do this time? I'll fix point F, I'll rabat point A, so, and I won't make a mistake this time on it. I'll fix point F there, I'll take point A, I'll rabat it until it's parallel to the vertical plane, project it up, and what am I moving? I'm after moving over point A to there. So there's F and there's the rabated A. And we label true length of FA. Let's take that true length in the compass from F, the diagonal that goes down to A, and let's use it from F down to A. Common position of A. I could do this part or skip it until the end. I like to drop them in as I go. We'll see more progress. What's next? We are going from F and we're looking for point E, because E is the one last piece of the puzzle here. So F to E is a true length as it's given right there. F to E. So we have F, searching for E, and finally I just use a different colour. I go with a brown colour here. I'm going from B up there to E. What do we see though? We see that that line is equal to that line. Both lines have to be equal in length, okay, because they're both the diagonals on this symmetrical surface. So the true length of the orange line is the same true length as the brown line, which is quite handy. Where's the true length of the orange line? It's already marked up here. And what am I marking it from? I'm going from B up to find point E, B to find point E. And shin for that, bit of colour to add. And there we go. That's the surface development of the four not sloping surfaces, three sloping and the one backing surface, I suppose, of this object, all found. Now I am going to, without teaching my way through it, I'm just going to solve my way through this one nice and quickly. So have a look if you like. The good thing about this one here is that the first shape is already shown for us, so that is quite handy, I suppose. How did they do that? Well, first of all, we have to recognize that AB, the first surface right here, the first edge AB is a true length, so that was projected down. The edge EF is a true length, so that was projected down. And then they seem just here to have taken the true length of the line, so they were batted from E, fixed point E, were batted around and move point A out. Take that distance on the compass and strike it from A down to E. You can see the strike of the compass. So E dropped. This was a random starting point and the distance was struck down. So I'm not going to teach the way through it, I'm just going to go ahead and draw it. And there we go, that's that question finished. So quick little run through that one. So more the same really, there's nothing new going on in that one. All true lengths, all true shapes. Moving back to SolidWorks now for our final question, and this time we're going to be transitioning from rectangle to circle, so a bit more difficulty coming in here. So one of the final ones here I'm going to go through, especially in as much detail, is just a transition piece that takes us from a rectangular profile here down the ground up to a circular profile up above. So again, probably among the harder of the developments you can get, but still it is nothing harder than any of the ones that we've done so far. It's just again more the same, you know, more true lengths, and that's it. To build this up though, if I did a loft on SolidWorks, it doesn't really look as good as it should. It tends to just take this corner up in the most efficient way it sees fit, taking it towards the center of the circle, and it gives me a fold most of the way up, and it just smooths out exactly on the curve around here. So I can't do it that way. That's not how we draw it. The way we draw it is this: we take them all as triangles. So we'll take a triangle up from the base up to one of the extremes of the curve here, and we'll have our four main triangles. So we have the one there on the right, we have the one there at the back, and the one here on the left. So we have four main triangles to take us up there, and then we have another series of triangles facing down. So this is how we break it up when we're going to draw it on paper. So that's why I modeled it on SolidWorks this way. So we estimate, just like when we're developing a cylinder or a cone, we break it up into with our 30-60 degree set square into 12 sections, and then we take the length, the linear length between point to point. So in this case here, we're going to be dealing with true length of a line, a second true length of a line, and then the true distance, just linear distance here, not necessarily true circumference, but the linear distance between point and point. And we just keep doing that, and it's just more and more and more of the same principle there chopped in. So to get the most accurate representation on paper that we can feasibly do as well within an exam setting, I suppose, where there's time restrictions, we break it up into 12 segments just like this, and we start putting our planes in, our triangular surfaces. So we just estimate them to be triangular surfaces like that. We just continue on this. So I'll drop in 3 more in this corner here. We've 3 more at the back around here, and finally, just to finish this guy off, the last 3 over here. And there we go. So there's the object broken up as it needs to be for us to be able to draw it on paper. That's how we do it. So whenever we transition from a circle to a rectangle, circle to square, or circle to circle of different diameter, we need to break them up similar to this. So using a variety of triangles to give a very close approximation to what the true lengths and true sizes are going to be. So that's what we'll be doing on paper soon. Now, on this example, similar to the last one that I did here, on this example, the back surface of the object, this blue surface right here, is vertical. So when we're looking at this on my worksheet there in a while, that back surface, if I just flick down to plan, it's a vertical surface. It's shown there as an edge view in plan, which means when we look in at the elevation, it's a true shape. So I can take the shape of that back surface and just drop it anywhere else on my page. So there I've shown it, and then I start to translate, or I start opening this guy up and showing the development. Now, what do we need though? We need a lot of true lengths. You know, there's a lot of true lengths involved here, which means there's a lot of rebatments. So what I've done there is I'm showing them now, fixing this point here and taking any edge and just rebatting them around into a position parallel to the vertical plane. So there's my true length of one of the lines. Now I'm not labeling them here in SolidWorks because it would be just next to impossible to keep up with these labels. But what have I taken? I've just worked on these back set of triangles here only, and I've taken them and I've rebatted 1, 2, 3 of them around and found them as 3 true lengths right here. I do the same then, I think next, yeah, I did the same on the front surface then next by putting in a plane there and rebatting all of those guys around and finding them as true lengths. So that would be this edge here, the edge of the purple, the edge of the green, and the finishing between the green and the dark grey right there. So they're all the true lengths, 4 at the front there, and I think I have 3 at the back. They're all the true lengths that I used in to go and do my development. And what happens from there? We start plotting out our points. Okay, and what do I mean by that? Plotting out the points. So to the left of the blue here is going to be the orange one. I got the true length of this edge right here, and I got the true length from plan of this small portion right here, and I struck them with my compass to cross each other. So I struck up with the first big true length and I struck across with my small true length, and that gives me the orange surface right there. The great thing here on SolidWorks is I can simply hit mirror. Now I know this is symmetrical. If we look down on top of it, the circular top opening is directly in the center of the object. So the orange to the left and the red to the right are the same. Similar here on the brown and the green are the same, and this navy and yellow are the same. Now next I have the orange done, which means I have an edge on the brown. I already rebatted this line here, the end of the brown. I rebatted it around, I take the true length and I take this distance, and we cross our arcs again. And you'll just see it's just repetition over and over, taking 2 true lengths, crossing them and drawing our surface. And again on SolidWorks it's great, I can just mirror it across, and it mirrors across to the green. And what did I say is next? It's this, I suppose you call it a navy one and the yellow one. So true length of this edge right here, taken and struck. So true length of the edge struck up, one portion of my circle struck out. I get my dark navy on the left and I get my yellow one on the right. Now, what's next though? It's this really light coloured one here, just light brown. Okay, so from the top point, that stays stationary. So we had stepped out 1, 2, 3 small spaces here up top. So we had gone out 1, 2, 3. And one thing to notice, they are not supposed to be straight lines. I think I might have added a curvature in on them at the end, but that is a freehand curve, not a selection of straight lines. But nonetheless, this point stays stationary now for a while because the surface, this triangle, grows in the other direction. It doesn't increase at the top, it stays where it is, but we need to find this point down below. So it's just like some of the previous drawings. We are going to go searching using true lengths from a fixed point and a fixed point to find this next point down here. So I'll just skip through the stages nice and quickly here. Got the compass, took our sizes, and there is our next one. What happens next? I need to go back up the same direction as I had started with there by adding in another triangular surface, this one right here, and again 2 true lengths, struck with the compass. Well, actually I mirrored that across first of all. 2 true lengths, struck with the compass to find our next portion. So you'll find that once you get into this, they're not bad at all. You know, it's a lot of repetition involved. After that comes this purple, 2 true lengths again. We'll find the purple one for me. There's the 2 true lengths. There's the surface, and mirrored across to the right hand side. Have we one more? We have this green, and then of course the pink on the other side. The 2 true lengths marked. Surface found. I mirrored it. Finally, this dark grey surface to the front, and you can tie it to the green or tie it to the pink, it doesn't matter. But again, like the first one, like this third one, oh, sorry, second, third, fourth, fifth one to the left and to the right, it can either go up here or it can go down here, whatever you prefer. So set your compass, strike your marks, and there you go. So there's the development of a transition piece that is transitioning from a rectangular base up to a circular top. I think really the understanding here comes from being able to visualize why we break it up and the format of these triangles, and then transitioning between all of these 3 facing down and then this one facing up. But I think the SolidWorks does a great job in just explaining what that is. And if you're not sure and if you're practicing, well, the best thing to do, draw it out, see if it's right. How do you see? Well, cut it out and try and make it and see if it folds around into the correct shape. Let's get back to paper and let's get this last one done. Now here we go on paper. We have a very similar style question set up to what we just saw on SolidWorks that we'll work through now. First move, the base is already labelled from A to B to C to D and then back to A, but I'd like to get the top of this broken up. The first thing I want to do is I want to show what all of them little triangles that I had on SolidWorks, I want to show them here on paper. So let's get this thing broken up. There we have that. I'm going to go labeling next. So I might just start with point 1 here, and I'll just work around in a clockwise manner because that's what I always do. Not quite sure if that's what I should do here or not, and we won't worry about it yet. We'll just get it all labelled all the way around. 9, 10, 11, 12, and finishing on 1 again. I'm now going to draw in the triangles, so I'm going to just start here with the front one, which is, it's lightly on my worksheet already, but you know, we won't have that set up for us in an exam, so I'll just set up that main triangle and I'm going to work around here now. I'll go clockwise to match my numbers. So A goes up to 2, A goes up to 3, and A goes up to number 4 there at the side, and then it stops because A can't stretch around and warp around to number 5, so it goes from 4 down to D, and then from 5 to D, 6 to D, and 7 to D, and then that stops and it goes a big triangular back surface which finishes with 7C, and then we go 8C, 9C, and 10C, And again, C can't stretch around to 11, so we go back down from 10 to be 11 and 12. I'm going to show what I can in elevation as well. Okay, just as much as I can at the moment. I'm not going to project everything up with big straight lines all the way up through. I'll just take 11 and 9 there, and I'll just dash them and label them 11, 9, 10 on the edge, 12 and 8, 1 and 7, 2 and 6, 3 and 5, and finally to finish there is number 4. Let's just draw a few portions in right now. And there we are. Over here then is B, C, and that's point A, D. And there we are. That is the first part of this question. At least we're set up and ready now. What we also need to, the big thing we need to really understand here, I think, is that the line that goes from B up to 1, right there, as it appears in elevation, B up to 1, is also directly in line with C up to 7, C up to 7. The big difference is C in 7 is horizontal, parallel to the vertical plane, so that's true length C7, but B in 1 is not. So we're going to have to just have a think about that after. They've given us a position here to start with, A and B. I'll assume, or actually I won't assume, I'll check. I'll check that that's the correct length, A and B. And is it? Yeah, that's spot on. The distance now that I'm going to start off with is this. I'm going to start off with, and you know what, we could just, and I'm not even going to look back at my SolidWorks, the color code here. I'm just going to really quickly drop some color on some of these surfaces, because I'd like to have it there just as a study guide really for yourselves at home. I'll be adding some color here and there. That red surface is made up of a true length of AB, and then we have A1 and B1. Okay, so that's what we are dealing with. So the true length of A1 or B1 has to be found by doing this. I'm going to actually work with B1. Where have I space? I'll have space for B1, I think. I'll take the line B1, and we're repeating what we've done for so many other drawings. We take B1 down to a position where it is parallel to the vertical plane. Some people just like to say it's horizontal, but it's parallel to the vertical plane. That's where B is fixed. 1 moves. 1 came across. So the new point 1 is there. That is the new line. Or not the new, that is the true length line. And I'll keep this really small now. TL of B1. So I can take the true length of B to 1, and I can strike it from B, searching for 1. I know it's already on the center. I also know A and 1 is the same length as B to 1, so I can cross them. Did it cross on center? It did perfectly. There's point 1. So we've made a start. We cannot put in fold lines, so just like any round objects, like one of the ones I did early in this tutorial, they don't have a fold line, specific lines. We just drop them in as construction, just like that. Next, I'm going to move on and get my next 2 surfaces, and I'm going to, because this is symmetrical, I'm going to work the surfaces 2 at a time. So we have this green one here at one side, and I'm going to run out of colours soon. I'll do as many as I can until I run out. I'll be running out very soon actually by the look of it, but we'll just get our 2 dropped in here. what I just realized right now is that the way that this is structured here on this worksheet, the fact that A is here and B is here means that we're going to be looking at the outside of the development anyway. We'll go with it. It's not a big deal at all. We should be looking at the inside, but it's okay. We've just taken that surface and we've dropped it flat down on our page and we have a true shape. Now I'm looking for point number 2. So we have, and again I'll just add the colour I suppose as I go. So there we are. We have found the red surface. We have number 1 and we're searching for number 2. So what do we need? We have a length from 1 out to 2. First of all on the compass. We take the distance from 1 to 2, which of course is the same as 2 to 3. And it's the same as 3 to 4. And it's also the same as the top of the screen one here, 1 to 12. Now, I want to get that accurate because I'm going to leave that set and use it all the time. That is point 1. Out to 2. I'm going to swing from point 1, searching for 2, but at the same time while I'm here I'm also going to search out here to this other side. I'm just going to get rid of that extra arc there. We don't want to get confused here, of course. I'm going to search for, what was the other one? Point 12. So I'm searching for 2 on the left, I'm searching for 12 on the right. Next, I need the distance from A up to 2 here. A up to 2, or I need the distance from B up to 12. They're the same. So I'm going to go with B and 12 because I've brought everything around here to the right for now. So I'll take the distance it appears here in plan, B to 12. That is it. We keep this as accurate as possible. There's 12 in the rebatted position. Project it up. And there's the true length of the line, B12. I'll take my true length of the line, B12. And I'll swing it from B and hit 12. And I also know that that's the same, it's symmetrical, so B12 is the same as A2. So B goes up there to 12 and A goes up there to 2. So that's 2 surfaces found. So much repetition going to be happening here on this sheet, as you can imagine, with all of those little triangles. Where am I now? I'm going to be adding the green colour there. Now I can't draw the top of it yet. As I said, it's actually a freehand curve, so I'm going to wait. I don't like freehanding until I have all of my points, so I'll wait until I get all my points together there, and all the points will be 1, 2, 3, 4, 5, 6, 7 I suppose around one way, and then it'll be 1, 12, 11, 10, 9, 8, 7 the other way. Okay, so once I have them all, I'll freehand them all together. But there we are. I'll add the colour as I go, just for understanding. Where are we next? We're going to move on next to the yellow surface here and beside the blue, which is point 3 up there, and the purple surface here on the right up to number 11, which I'll be looking for in just a second. So there are my next points I need. First off, distance from 2 to 3 or 12 to 11, whichever way you want to go. So we go from 12, searching for 11. We'll go from 2, searching for 3. I need some true lengths. I'm going to go from B to 11. So I've already struck one arc for 11. This is going to be my second one. That's the true length of the line, 11. Now these are all getting so close to each other, so take care. We get B to 11. and we strike B11 and A3. With a colour. So, next, just maybe the second last one or so before I start fast forwarding through the video, I have my brown here on one side, and I will go with orange on the other side. I think you know what's coming. Take the distance 3, 4. From 3, searching for 4, which is the same as from 11, searching for 10. And then, where are we? True length, B10. We'll draw the line B10 and we'll set it, and we'll find it in our development. B finds 10 and A finds 4. B finds 10, A finds 4. Now, before I decide to just forward through the rest of the video, I'm going to add one final surface in here, and that is just this. I'm going to just put a darker green on this one right here, and I'm going to go ahead and add that surface in, and of course that is the same as the one here on the right based on B, same surface, so I'm going to add the same colour on both. Now, what do we have here? So I'm looking for point D. I have A and 4 already at the end of the orange. I'm looking for point D. Well, A to D is true length already, so I'll strike it. A looking for D. Now, what we don't have though is D to 4 is not a true length, so I'll rebat it. And this time, just because this side is busy enough, I'll take it over the other way. D is my fixed point. Point 4 there, just kept the same height but moved, and that's 4. So the true length of D4 is here. Set D4 and take it from 4 down to D. And there we are. While I'm set, I know that D to 4 is the same as C to 10, so I'm going to strike from 10 down there looking for point C someplace. What else? I have B to C, of course, as a true length there sitting on the ground, B to C. Now, I think I might just forward through the rest of the video nice and quickly, because it is so much more repetition of the same principle over and over, and then at the end I might just check back in and have a quick little chat and see if there's any last points to go through. Second last job is to find point C. So we have the very front surface. We have wrapped around 3 left, 3 right. So we have 3 small left, 3 small right. We have our 2 green surfaces, green and green, and we have 3 on to the left, 3 on to the right. It's the back surface that appears there in the elevation, and the portion of the elevation that appears as a true shape, which would be, if I just dash it in there maybe, that hatched area right now appears in the elevation there. That is the remaining surface on this development, and the distance shown there in elevation is all true. So I already have 0.7 up top. I'm just looking for the point. Which one would I suppose I'll put it on this side. It's my only choice really. I'm looking for point C. So the distance from D to C, struck there. And I probably have to go bigger with that again maybe. Don't know where that's going to be. And what do I have then? Well, I need the distance from 7 to C, and that is a true length. So 7, C is already given there as a true length. 7 to C. And that right there is a seam, or seam edge, and that is a seam. So those two will end up being stuck back together or welded back together or whatever it happens to be. Now the very last job on this question is freehanding the curve, joining all of those points that I've just constructed, and if I'm brave enough to, I can even go back and finish off adding the colour up at the top of each of those triangular areas. And there we have that complete question. Now, if you have a nice set of colours at home, it might be great to just go ahead, continue on the colours as you go around, or maybe hatch out some or shade them in some way, and you'll see them referencing onto this. As I said, the only thing I don't really like about this is the fact it was set up there. I should have maybe changed the lettering, but I don't want to confuse anyone that's relatively new at this topic. But we should be looking at the inside of a developed object, but in this case we're looking at the outside. That is it for advanced developments for now. So there's some intermediate ones there to start and some advanced ones here to finish on transition pieces. We have a little bit of envelopments dropped in there as well, and I hope you found this video to be quite helpful in your study of the topic of surface developments. There'll be more coming on the basics and on some more intermediate tasks, but for now that's it. Thanks very much for watching.